Hello everyone, welcome to this video. This video is a continuation of my series that I just did, which is a series of 6 films, I think, about where I built a library or a module for Python for solving ordinary differential equations, or ODEs. And this video is sort of a continuation of that, but at the same time, you can watch it without watching all those videos. That'll be fine as well. Before we get going, I just want to say that there's only a small fraction of the people that watch my videos that are actually subscribed. So if you do like this video, do consider subscribing. It will mean so much to me. Subscribing is free. You could always unsubscribe. So let's jump into the video. So in this video, we'll be considering a very familiar system. You should know it well. It will be some box or some spring which is attached to a box, and it can bounce up and down, and it will be fastened at a point that will be able to move. So we'll call the position of this point W, and it's a function of t, and somewhere around here y is equal to 0, and this spring will have some length L. So all the way down to the middle of the box, the length will be L, which is the length of the spring at some sort of equilibrium point, and the stretch of the spring, which will be also a function of t, and of course plus the half of the length of this box, which is some value b. So, as in all problems in mechanics, or as you're used to in your introductory physics class or whatever, we always start by drawing all the forces on this system. So we'll have some spring force, which might be pointing upward, Fs, and we'll have some gravitational force, Fg, and we'll also draw some other force, Fd, for where the D can stand for drag or dampening or something, because we want to eventually include that as well, and that force is usually in the opposite direction of where the box is moving, right? So from there we simply say that we want the sum of all the forces. You should be very used to this if you've done some physics at all. Fg plus Fs plus Fd. Simple enough. We can write all the forces up. So Fg is, let's say that upwards is the positive direction of the system. So Fg is minus the mass of the system, or the box or whatever. So it has some mass m times the acceleration of gravity, and our spring force is some spring constant k times the stretch of the spring. Usually write this k times x, but let's call it s for now. And then we have some dampening, which is some parameter multiplied by the change of the stretch, which can be seen as sort of the velocity of the system, right? I think it's important to think a little bit about what this means. So when this bit, ds dt, is larger than 0, what is happening is that the stretch is increasing, meaning that the box would be moving downwards, right? And in that case, this force, represented by this term here, would be pointing in the opposite direction, so that will be upwards, just so we have some thoughts about that. And what we want to do is, like in all of these types of situations, is apply Newton's second law, right? Before we do that, let us write up everything we need to know about the position of the actual box, all right? So the position would be some y, which is dependent on time. It will depend on the position of the anchoring point, w of t, and because it's the position is actually in the negative y direction, it will be minus the length of the spring plus the stretch of the string. That makes sense, right? And also minus b divided by 2. So that will be the center of mass of the box. And then we can think a little bit more about this. What will be the acceleration be, right? So that will be, I think you should all be used to this. The second derivative of y in t, which will, we can simply just take the derivative of all the time-dependent terms here, yeah. So that'll be d dt squared and minus ds dt squared, because those are the only terms that are actually explicitly dependent on time, so that's the only terms that we actually care about, yeah. And so what we know is that the forces that we add up here, we have these up here, must equals m times this acceleration. So we could just write that up. That's minus mg plus ks plus beta ds dt equals m, and then times this term up here. There you go. And that should be it, yeah? What we want to do now is we want to rewrite it a little bit. So we'll bring the second derivative of s here over on the left-hand side. ms over on that side first. And then we'll have mass w. That's what's left. That's what's left up here, yeah. And that'll also be the second derivative. And then we'll have move the mg term over to the right hand side, and we will move the beta term. That's only, and the only part that's left is the Hooke's law term, right? So that'll be ks. I think I've got it all there, yeah. So, and we'll also divide through by m. These will disappear and we'll get an m there, right? Because we want to use this framework that I've written, that you might or might not have implemented yourself with the ODE solver library in Python, we want to express what we're trying to, our solution with the letter u. This equation here will turn into an equation with two parts. It will be a system of equations. So what we'll do first is we'll say that, okay, we'll rename s into u, and we'll rename the first derivative of s to, so this will be u0, and we'll name this u1, and then we can express this as a system of equation by putting both of these into a tuple or a vector containing u0 and u1. So the first of these equations we'll simply write as, all right, we have du0 dt, so the first this bit, right, is simply equal to u1, okay? And furthermore we'll write that du1 dt, now that's the you see now, because u1 is actually the first derivative of s here, this will be the double derivative of, the second order derivative of s in time, yeah? So that means that we can, this will equal this part over here. So that'll be w, the second derivative in time, let's just look at that at the same time, plus g minus beta divided by m times, and here we have the first derivative of s, and we have renamed that to u1, so we'll write that instead. So here you see the linking of these two equations there, and the last term is minus k, oh, it's a b, divided by the mass again, and here we have an s, which we have renamed to u0. So that'll be u0. So here we actually have two coupled differential equations which we will be able to solve with our ODE solver framework, which is able to handle these types of equations. So they look a bit different now. We'll be able to solve this in a stepwise numerical fashion, even though we have this interdependency represented here, that we have a U1 in both of them, and there's U0. So before we actually start programming, I want to show you that I've actually added, so this is the GitHub repo, github.com/gregwinter//YouTube. So this is where I'll keep all my all the code that I have been writing in these YouTube tutorials. Here's the ODE solver library that we'll be using, and everything we need is in here. You won't be implementing this now, but I have made it possible for you to install this this module with pip. So I could simply pull up a terminal here. This is in a folder called random shit. You can be anywhere, but you could simply write this this little incantation here now. So let me just copy that like that, and that should install it. Yeah, successfully built. So now if you pull up a Python terminal, you should be able to import ODE solver like that, and now you should have access to both the simple forward Euler scheme and also Runge-Kutta 4, the fourth order Runge-Kutta, like that. So that is what we'll be using. Very neat, right? Okay, so here I am in an empty program, and we are going to write a problem class representation, what we just wrote down, right? So we'll call this oscillating system, or OSC system, like so. What we'll do is we will type up the two equations we're solving. So we have a system of equations. And that's it, actually. So what we'll do, we'll type up a constructor in it, which will simply we'll just give it all the parameters. So that's m, the mass, the dampening constant, and we have a spring constant, and we have the gravitational acceleration, and we have w, which will be a function. So all of these other, everything here except this w will be some number, a float, and the rest of them will be, or well, the last one, w, would be a something that's callable, right? A function. So we'll type up self.m, self.beta, self.k, self.g, self.w, and these will be, yeah, simply the numbers. So if you're writing Python 2, which I hope you aren't, you should probably wrap these in floats like that. But I don't think it is necessary, because if you pass an integer and it will be an integer, you'll have these division errors. But yeah, we won't write it like that. And what else is there? Yeah, G, K, G, and W. So that's that. And that's really everything we need. So we can specify, when we create an instance or an object of this class, we're able to specify all the parameters, and then we'll use the ODE solver to solve them. So, but we also need to call, make this callable, this class, so Python will see it as a function, really. So if we insert some u, which is 1 point of our solution, so that is 2 values of these 2 equations up here, right? 2 right-hand side values, really. And a corresponding time point, we should get some values out. So we want a u0 and a u1, comes from this u. These are both contained in this, so let's unpack that first. And just to make everything a bit easier to write, we will extract all these values. There. So that's m, beta, k, g, w. And these are class parameters contained within the class, right? So there. Yeah. I just couldn't be bothered to type it up. But now we don't have to write self.m or self.beta all the time. So, and now what we need to do, now this is a bit of a trouble because here we actually have a second derivative within one of our equations. So what we'll do is we will approximate the value of this second derivative in time of w by some finite difference scheme. Okay, let me just show you what that means. So the definition of the derivative of some function depend on x is the limit where some h goes to 0 of the function x plus h minus f of x divided by this this h, tiny number. So that's, but we can approximate the value numerically by just saying that h does not approach 0 because we're not able to compute that, but say that h is just some very small number. So we can just write the exact same thing. All we know is that h is small and not necessarily 0. So that's an approximation of the first derivative, right? And this is exactly what forward Euler is, which I've talked about numerous times. But we want to approximate the second derivative. So this will be exactly the same as going backwards instead of forwards. So we could have f of x minus f of x minus h divided by h. Those should be the same as h approaches the infinitesimal limit, right? So now we'll use sort of apply this approximation again on this to represent the second derivative. So we have f double derivative of x, which will be first this guy, and then we'll go backwards. So it'll be, first we'll have x plus h minus f of x divided by h. So that's one derivative. And we'll have minus f of x minus f of x minus h. There you go. So now we have sort of applied the numerical approximation of the derivative twice, once backwards and once forwards. No, sorry, forwards and backwards. We can simplify this expression and you'll see that we will get a much more neat expression. It'll be f of x plus h minus 2, we have 2 of these, 2 of f of x, and then plus f of x minus h. And you'll see that we'll have h squared beneath the fraction line there. So that will be our estimation of the second derivative. That might have been a bit quick, but you can stop and think about it a bit for yourself and I'm sure you'll understand it. But that is the finite difference central, is what you call it, the central approximation of the second order derivatives. Type that up so it's clear. So use finite difference for the double derivative of w. So we'll write dw is equal to, now remember that w is a function. So we'll call that, so here we have divided by, so we'll specify some parameter LH and divide by the square of that. So we'll just specify that in the constructor here, I think, self.h, and we'll say that that's just some small number. I'm sure we could go smaller, but I think that will be good enough. So what was this? We had t plus self.h. T is the t up here, and then minus 2 times the function that we just wrote at the same t, and then plus scroll up a bit so you can see what I'm doing. There, plus the function again evaluated at t minus self.h. Okay, so that's everything we need. And now let us look at the right-hand side of our equation, and this is the only thing that we need to return because that's our estimation of these two derivatives. And as we keep going, solving these iteratively, these will update, and we'll have our solution as a set of points. So the only thing we need to return is, it has to be some sort of NumPy array, I believe. So we'll probably need to import that. So import NumPy SMP. And let's go down here again. Yeah, and then we'll U1 was the first right-hand side, as you can see up here, and we'll also return what is the right-hand side of this, and that is our dw, which is our, well, it's actually the second order derivative, so let's write d derivative of, yeah, whatever, plus g minus, oh sorry, in a comma there, minus beta divided by m, what else, and that was supposed to be multiplied with u1, and the last term is k divided by m times u0. Okay, k divided by m times u0, and that should be it. Then now we have typed up our entire program, our entire problem. So what we want to do now, of course, is to test it. So we'll write some test function down here. Whoops, there. We want to plot it, so let's... first we need a solver library, so we'll import ODE solver that we just installed, and we'll import pyplot from matplotlib. Right, and whenever we have written an algorithm or something up, we want to compare it to something that is analytically solvable as well. So we'll have some sort of benchmark, right? In this particular system, that when the mass is equal to the spring constant and it's equal to 1, as well as when this dampening constant and gravity and our point where our spring is fixed is equal to 0, so we won't have any gravity now, then we have an analytically solvable situation. This simplifies our set of equations quite significantly. So the derivative of u0 will be the same, u1, but our second equation, the derivative of u1, will be minus u0. And this coupled set of differential equations is that's a very neat solution if we provide the proper initial conditions. So if we provide initial conditions that u0 at time point 0 is equal to 1 and u1 at time point 0 is equal to 0, well, then the solution to this particular problem will be u of 0 of t equals cosine of t, and u1 of t will be minus sine of t. And if we remember, this will represent the position of the spring stretching, the cosine function, and this will be sort of like the velocity. This will be our benchmark case. Okay, so we'll try to look at that first, and then we can experiment a bit after that. Okay, since we'll have an oscillating system, we will want to run it for some set of periods. So let's do 4 periods, and each period, or the full time, will be, well, one period will be 2 times pi, because that's a full cycle, right? So periods times 2 times pi. Okay, and we also need a number of time points to solve for. So let's say that we go for 1,000. Okay, and then we can define our problem. So this will be the oscillating system. And what did I say? It will be a simple situation where the mass is simply 1, beta was 0, k also 1, gravity also 0, and this w, the function, will be a function that returns 0 for every t. Okay? And then we also want to write down some initial conditions. So that'll be 1 and 0. And our time points that we'll be solving for will be a linear space from 0 up to t, which is the end of the entire simulation, and for all these n points. So we'll plot a figure. Okay. And yeah, I want to compare the two solver classes, both forward Euler and Runge-Kutta 4. So for solver class in, I'm sure you'll be able to see it. Yeah, you know what we'll do? We'll import them more directly. So we'll write from ODE solver import forward Euler and the fourth order Runge-Kutta. So, and then we can say that we want to solve both with forward Euler and Runge-Kutta. So our solver will be the solver class, and we'll give it f, which is the problem. So because this is callable, this will work, hopefully. Okay, and then we will set some initial conditions, which will be the initial conditions that we wrote up on line 30 up there. And we want to, yeah, and then we simply go ahead and solve it. So we'll have a u, which will be the solutions, and t. And then we go solver.solve for these time points. And now we would like to plot it, I think. So we'll plot it in two figures. So for each time, each iteration, it will only be two iterations. We will make a new figure. So we'll keep that inside this loop, figure there. And then we'll plot t, and we'll only do the first part of this u, because that's actually the position of the spring stretching, so that will give us the solution. More or less the mass center of the box. I say more or less because it's just some shift, right? And we'll label this with, we call this numerical. And we will plot an exact function as well, because we know the solution, right? I just wrote it up. T, and the solution is the cosine. There, so we can compare it easily. And we'll label this as exact. We'll show a legend, and we will also add a title of these two. It will be two figures, and the title will be the name of the solver class. Yeah, so it'll just be solver class dot name. There you go. That should work, I think. Then all we need to do is, when the loop is done, we need to show this. Okay, it's time to run it. So we'll go Python oscillating system.py, which is where we are, and see if it works. It doesn't, because I'm missing a comma on line 11. There it is. A bit of debugging for you there. Okay, let's try again. I'm missing another comment because I copied that line, and this is on line 16. Yeah, that should be reasonable enough. Yeah, all the way at the end there. I think that's good now. There you go. So now I have two figures here. So if we look at the forward Euler solution first and compare it to the exact solution, we see that it actually gets more and more wrong as we progress further into the future. But if we look at the fourth order Runge-Kutta, we see that we're doing very good actually. And this is interesting because well, it's not that interesting. We know that this is more exact, but here we actually see a very nice evidence of it, right? So that's cool. I really enjoy this. Yeah, nice. Yeah, I should not have written this figure here. But now let's do something different, okay? Let's actually make this into something interesting. I think we want a different... Yeah, let's do something with this. So we don't want this anymore. What we want is something a bit more exciting. Oscillating system. And now we'll add... Okay, first of all, let's just add some damping. Okay? So we'll go 1, and the beta will be 0.1. Same spring constant, and everything else the same. There. So now we have both of them, so we can compare them when we're done. And then it will actually make sense to just keep what we had already. So, yeah. Let's go. Yeah, okay, because we have a dampening now, the exact solution won't be the exact solution because this will, well, be without dampening now. So here we see that forward Euler, yeah, it gets the amplitude of the oscillation decreases as would expect. And here is the Runge-Kutta one. So these are not entirely equal, I think, but now I think it would make sense because we don't really have an exact solution anymore to not plot this and to put them both in the same figure to compare, because we know that the fourth order Runge-Kutta would give a more correct solution, right? So I think we would be interested in comparing these two methods. So now instead of two figures, we'll just do one. So the plt.figure function will be outside the loop, yeah. And we will plot each solution in the same one. So t, u, the entire, all time points, but only the first one because that's the position, yeah. And we'll label this as the solver class name. That will make sense now. And we'll add a legend after the loop. Yeah, let's go. So there we have compared the two numerical solutions, and here we see that yes, there is some stuff that they don't agree exactly, yeah, as we would expect. And we have reason to believe that the fourth order Runge-Kutta method is better than forward Euler. But yeah, let's continue with that. Now let's add a driver. Let's actually change the position of the anchoring point of this thing, right? So in order to do that, we need to write a function for W. Okay, so, and it'll be a function in time. So we want this guy to oscillate only at certain times, because I think that'll add energy of the system. And it's a bit odd right now because now this isn't really a force, this is just an acceleration. So this is an acceleration, so it'll accelerate the system, but that's exactly what a force does. So it's I guess you can look at it like that, except you can't. So what I want to do is, if our t is larger than a fourth of the way in and less than halfway in, then we will pump the system, do some stuff. So it should be at some frequency. So let's just add a cosine function, and else we'll do nothing. So let's try that, but let's do the one without dampening first. Whoops. So we'll copy this. It'll be almost exactly like this, except now we will add this W up here, yeah. this should be that. Everything else should stay the same. We want to compare both the solvers. So let's go. And there you are. So yeah, let's let it run for a few more periods. So let's go to 10. We might have to do more points, but yeah, let's keep it at 1,000 first. Okay. Oh wow, look at this. So this is sort of what I assumed would happen. We have some oscillations going on, and then 25% of the time into our simulation, we start adding energy to the system. So we see that the amplitude increases, it ramps up here, yeah? But we also see that it should switch off this driving force, right? Halfway in. And then the amplitude should stay the same again. But the only solver that's able to do this is the fourth order Runge-Kutta solver. I think the forward oil might be able to do it if we add a lot more points, but it would take much more time. So this is actually interesting to see how much better this algorithm is at solving these types of systems. So let's just add a bunch of more points to see if it's able to cope. First, here we go. It takes a while now. So this is the forward Euler solver, and you can actually see how many iterations per second it does. Yeah, I think that was too many time points. Let's go to 10,000 instead of 1,000,000. Okay. Yeah, there you go. So the fourth order Runge-Kutta solver is slower, as we see. This is a good example of, but it should be much more precise. But this is enough for the forward Euler as well. Only at the very end here we see that it starts to struggle a bit up here. Yeah, see a little blue there. I tried to actually, there are many points here, so my computer is not coping. But yeah, that's cool. And now let's add some damping and this special force, but we'll 10,000. That's more than enough. You know, let's do 1,000. See how bad this is. So now we'll add a dampening force as well. Maybe we want some gravity. That is, which argument? This one, I guess. See what happens. Okay. First of all, the initial condition probably wasn't that good with the gravitational problem, because it falls down first. So it actually stretches out a lot, and then it sort of goes in, and then we have the driven oscillator. But it's still interesting to see, you know. It's a bit messy, so just remove gravity. It's funny that you can do that in a computer. Let's remove gravity. We have a lot of freedom here compared to what you'll do in pen and paper. Here you go. This is a nice one. So here you see that it starts out oscillating somewhat not that excitedly, and then we have added a driver. We drive the energy up, so we have higher amplitudes, as you see, and then the dampening takes effect again. And you see that they don't agree all that much, the two methods. So this is fun. I will of course add this script as well to my GitHub repo, and I'll link to it down below. And if you have any questions, just ask them. I will try to answer them. I'm not too good. I know I'm not too good to answer questions on my YouTube channel, but I try to. And you can play with it yourself. So now we sort of saw that we have built an ODE solver library that we can apply to some systems that are a bit difficult, like this one. And we also show that, well, we're able to do stuff that you cannot do with pen and paper, which is nice. And it's fun and it's fast, you know. Actually, you could do it with pen and paper. Then you had to sort of compute the do it in this sort of way, you know, iteratively, one time step at a time. So that's very tedious. Anyways, I hope you enjoyed this video. I will try my best to make more if you like them. So give me a like. Take care. Until next time. Bye.